Good afternoon. I apologize for the original speaker for this slot couldn't make it, so I came instead. The first slide, which you have to read in detail, is basically saying these are intentions but not promises. The enterprise data center it's all about open interfaces. It's not just OpenISA. It's other features of the processing system need to be open as well. This is talking about making the a cache coherent interface open. So we have a RISC-V multi-core processors connected to this, or persistent memory interfaces, or accelerators connected via PCIe or OpenCAPI or other. And this is the OmniExtend, which is the memory protocol interface for enabling memory-centric architectures. So it's a coherent interface. So there are planned open source contributions in this. The first one is the Western Digital first core Swerve, and then the microarchitecture introduction, performance benchmarks. And then I'll talk about the OmniExtend protocol. Vision for the future data center CPU architecture. We have multiple RISC-V cores with cache controllers, all connected via the what's called Uncore, which is the system on the chip connecting to cache coherent interfaces to either DRAM, persistent memory, PCM and MRAM, and then the have Gen 5 PCIe, for example, OpenCAPI. And we can also connect an Internet 802.3 physical interface. So medium performance out of order RISC-V core. We can have a standardized and open JEDEC interface architecture. This NVDIMP, which I actually worked on at my last job for high density emerging non-volatile memories. There's support for high bandwidth and low latency accelerator interfaces, supporting machine learning and inference engine accelerators, support for standardized memory, protocol fabric, for instance, OmniExtend, tile link over, which is implements tile link over 802.3, allowing coherent scale out for memory-centric architectures. So we can connect several of these systems together through the 802.3 interface. If you need more than two, you need to go through some sort of switch, and we can use a programmable switch, so which is protocol, understands the protocol, so we can actually implement part of the protocol on the switch itself. So it allows large number of RISC-V compute nodes to connect to non-uniform shared memory using standardized and open coherence protocols. And we can have a memory appliance with aggregation and disaggregation also attached. Okay, and then we can have replace some of the normal processor nodes with DRAM appliance or non-volatile memory appliances. So we can go to direct to cache, access caches directly over a commodity fabric, the 802.3. Memory fabric may mean different things to different people. Could mean a page fault trap leading to RDMA requests, incurs context switch and software overhead. Global memory translation management in software leading to load stores across global memory fabric. Or coherence protocol scaled out, global page management and no context switching. Memory-centric architecture with OmniExtend allows, this slide has happened before, but that's, we've done that one and done that one. Okay. OmniExtend memory-centric fabric architecture. It replaces Ethernet level 2 with serialized tile link messages. It keeps the standard 802.3 level 1 frame. And it interoperates with the barefoot Tofino switch and also future OTS Ethernet switches. Custom frames are parsed and processed in the P4 languages. The barefoot Tofino switch is programmable. And it enables stateful message processing inside the switching fabric. And it supports innovation required for reliability, availability, and serviceability. And it can be an FPGA or ASIC switch. It's not limited to 802.3. You could use something else. The protocol translation and modification in such a programmable switch needs no new silicon. We have 100 gigabits per second available today on 802.3. And there's a clear roadmap to 200 and 400 gigabits per second with 56 gigabit PAM4 and 8 lanes. So this is a picture of the demonstration of this protocol running at the Santa Clara Summit. What you see here are two processor boards with the blue handles are actually connecting the Ethernet cable which connects the two. And that's where the OmniExtend runs over that cable. And it's, you can't of course see it here, but on the there you could see that the processors were accessing unified the memory across the two boards, and both processors could access each other board's memory coherently, accessing the other processor's cache if necessary. And the binary is on GitHub. These are measured latencies plotted against the test size. And for the smaller test sizes, the task fits inside the cache, so you get cache hits all the time. And then as the test size gets larger, you start seeing the memory access latencies. And you can see that without a single socket, without this OmniExtend, you get access about 70 cycles. But when you connect up to the other board, you increase your latency even to your local memory because you have to query the other processor's caches. And then you end up with the memory latency added to that when you access the remote memory on the other board. So, routing OmniExtend through the programmable switch. Use the barefoot Tofino ASIC. It's a 64-port, 100 gigabit Ethernet switch. 6.4 terabits per second aggregate throughput. There's no shortage of bandwidth. And less than 400 nanoseconds latency. It supports the hardware description language called P4. So it's the successor to OpenFlow, enabling protocol innovation. You can start programming what the switch does by writing code in P4. So we describe the tile link message format in P4, and we have what's called a match action pipeline, also known as flow tables. It enables line rate performance on that P4 code. And we have modifications, to coherence domains, protocols require no new silicon. You can sort of, for instance, partition the system and program the switch to restrict where messages can go. You can use an FPGA switch for more exotic experiments, but we've been using the Tofino switch. And eventually, when everything's working, you can generate some custom silicon to really optimize the latency and the number of ports. So this is the proposed OmniExtend innovation platform with lots of different Ethernet interfaces, these different abbreviations of different sorts of Ethernet interfaces. and then we can plug in the DRAM and the CPUs and accelerators into that platform. The message is we need to open up the coherence fabric as well as the ISA to really get open computing working. Thank you. Are there any questions?
Hello, can you hear me? Thank you so much. Would you mind to go back to a slide that shows the live development board with photos? Previous one. There's a development board. Yeah, this one. So my question is this open source in the GitHub?
The processors are, I believe, Sci5 designs on implemented on FPGA, which is why they have those heat sinks and fans on them. I don't know the standard, how open the sources are for the various components.
Next question. Another slide, you show a very interesting setup. You are using 64 ports, each with 100 gigabyte the setup. In that slide, can I say that you are trying to do high-speed internet? I mean the Ethernet network interface to use the RISC-V technology to build a high-speed networking. That's here's next slide. Next one, sorry. Yes, this one. So from this slide, I can see that there is 64 ports. Each is 100 gigabyte. So are you going to do some high-speed networking experience or something?
Well, 64 ports allows you to connect 64 processors to it, or 64 things. So we haven't yet started even trying to go anywhere near that size. It's just
so this thing is quite interesting. 6.4 TB per second. This really high-speed transmission.
yes, it's
Could
really
you
nice.
will you tell more about that? This very, very exciting thing in my mind.
Because you need bandwidth when you do cache coherence.
So let me just add some commentary. So what Western Digital is doing is actually, the picture that he showed you was point-to-point.
Okay.
So we're actually working on the implementation to go over a Tofino switch. So the first one will probably be like 10 or 25 meg Ethernet, but ultimately we know that this 100 gig switch is available. So we're working right now. We have some enhancements that we have to make to the cache coherency bus, which is tiling today, but we need to make some improvements so it works in an enterprise or in a more robust format. So we are working on that. What is on our GitHub site are just binaries, not the source. And we do have the specification on the site. So the point of what Paul was saying is we want to promote a coherent fabric and something that we can deploy in a short amount of time. Okay?
A final question. Your sharing is so exciting, especially focus on enterprise usage to apply RISC-V technology for enterprise. Actually, I'm the enterprise user, you can say that. We use a lot of data center equipment server. One critical component from my personal point of view is that we heavily rely on Oracle Java. So Western Digital also work with the society or community to work on to port the OpenJDK or the Java to enable us to migrate our huge applications on Western Digital's enterprise CPU based on the RISC-V.
I'm not sure I got all that. Are you talking about porting Java to?
Currently, we are the enterprise user. All our applications rely on Oracle Java or OpenJDK. So these are one of the critical components. I can see that from the desktop, there's good progress to port the Linux.
Yeah. I'm not sure I would be surprised if Java doesn't get ported to RISC-V, but I have no idea. It's not my field at all.
Thank you.
Thank you for the talk. One question that to fully utilize or to fully take advantage of this new design, what is the programming model? Do we need to change how we write programs? The system software, do we need any change to the system software?
For the multiprocessor system, it will merely comply with the RISC-V memory model, and you just program as you would any RISC-V multiprocessor system. Of course, you have to take into account the latencies, so you have to take into account performance, but the programming model should be exactly the same as if it's as any multiprocessor RISC-V.
Also, one question for one of your slides mentioned about the page fault mechanism in OS. So I imply that you use the event paging mechanism in OS to make use of the remote memory.
I think that's more that this represents an alternative approach, which is just making all memory accessible by the same mechanism, which is you map every processor can access every other processor's memory. It's just one flat space.
During this talk, so I just checked on the website. So Western Digital is also the member for in Gen Z, right? So is there any overlap with OmniExtend? Those are Gen Z is also memory-centric architecture. Yeah, that's my first question.
So just to respond, yes, we are members, and I think we're on OpenCAPI and probably 4 or 5 other interface fabrics. So the reason, just a really quick answer, the reason that we had proposed OmniExtend and we're working on it is because we can deploy silicon much quicker. Right? This is the challenge of all these other interfaces that are out there. They're either not really open, they're kind of open, but not, or they're using these bizarre PHYs that cost a lot of silicon and other development. So there's kind of a combination of challenges with these other interfaces. We are just interested in having something that's open, right, at the end of the day. So OmniExtend is just our way to really push. And if at the end of the day it doesn't win, but some other interface wins, great. But to date, we have had a lot of people asking us to collaborate on this. So we hope to develop it further.
So my second question is, how long do you think we can have this kind of rack scale, Datacenter scale with my processor?
Can you repeat that?
Okay, how long do you think we can have the rack scale, Datacenter scale with my processor in market?
Not fast enough. I don't have an estimated time for you. We Western Digital did form with Google and some other companies, including Sci-Fi and Esperanto, a group called CHIPS Alliance, which is an open consortium to do development for SoCs to help accelerate and have companies bring devices like that potentially to the market.
My name is Carlo Italy. So would you show me the next slide? Sorry, maybe one previous. Sorry. Access latency kind of stuff. Yes. So I have 2 questions. My first question is very simple. On the horizontal around 16 kilobyte, 32 kilobyte, 60 kilobyte. So single socket, red line is slower than NUMA remote memory.
So
So red line?
yes. That is without any, that's with a single socket, there's no OmniExtend at all on it.
But it's slower than NUMA remote memory. I don't understand.
So if you've got a single socket, you've just got just one board with its memory. With two sockets, you have NUMA local memory. Then you have a non-uniform memory system.
The single socket is slower. Is it right?
No, this is latency. Latency, it's not latent. The shorter the latency, the higher the performance. This is latency, not performance, the graph. So it's the lower the better.
But the red line is larger latency than NUMA. NUMA local memory is NUMA remote memory is faster.
No, NUMA remote memory is slower because it's higher latency.
Okay. Okay, my first question is Uchu. I'm not the server guy, so would you comment on any performance perspective comparing with existing platforms such as Intel?
Performance comparing with what?
Yeah, performance expectation or perspective.
I think it's a bit early to go into details of performance.
Thank you.